Hello, this is Tariq Masoud. I am assistant professor at Wisberg Division of Engineering at Marshall University. Today I will be reviewing some material for FE exam for mechanical engineering, and the section I am covering is about electricity and magnetism. The material I'm covering came from this textbook, which is FE for mechanical. Just giving you different practice problems. So I will be solving few practice problems about electricity and magnetism subject. So let's get started with the first problem. The first problem is about electrostatic fields. Simply as you can see here, the problem said if you have two charges and there is a distance between them is 10 meter, and there is a point of interest P between the two charges, and they said the electric field at the point of interest P due to the two charges equal to 0. So what's the most nearly the distance x between the first charge, which is 0.001 coulombs, and the point of interest P. Now, in order to answer this problem, you need to understand that the electric field at point P is the summation of the electric field due to charge 1 and charge 2. Since the net electric field at point B equal to 0, that means the electric field due to charge 1 equal to the electric field due to charge 2. They are same in magnitude and they're opposite direction. That's why when you add them up at the point P, at the point of interest, you will find the electric field equal to 0. So having me said that, now we just need to find what's the electric field due to charge 1 and the electric field due to charge 2, and we put them that are the same, and we solve the equation to find the distance x. So let's draw the problem first, and we understand what it is. So this is charge. This is charge. This is the charge 1 Q1, and let's assume here that's the charge 2, and the distance between them is 10 meter, where charge 2 is 0.003 coulomb and charge 1 is 0.001 coulomb. Now the point of interest between the two charges is P here, where the distance between Q1 and the point of interest is x, so we need to find what's that x, and clearly that this distance between Q2 and P is 10 minus x. Okay, now let's find what's the electric field. The electric field is the force applied per unit charge. So there is electric field at point P due to Q1, so that's E1, which is Q1 over 4 pi absolute, which is the permittivity times x squared, where x is the distance from the charge Q1 to the point of interest. And that's, if we substitute Q, that will be 0.001 over 4 pi absolute x squared. Now, the electric field due to charge 2 at point P is E2, which will be Q2 over 4 pi absolute, and the distance between Q2 and P is 10 minus x squared. So if we substitute Q2, that would be 0.003 over 4 pi absolute, is the permittivity 10 minus x all squared. Now we said since the electric field at net electric field at point P equal to 0, that means E1 equal to E2 in magnitude. So if we do that, we'll find 0.001, which is the electric field due to Q1, equal to E2, which is 0.003 over 4 pi absolute 10 minus x all squared. Now, if clearly we can see that term 4 pi absolute will cancel out, and also if we multiply both sides of the equation by 1000 to simplify, so we will have 1 over x squared equal to 3 over 10 minus x all squared. Again, all what I did, we just multiplied both sides of the equation by 1000, so we simplified the equation. Also, for the term 4 pi absolute is cancelled out from both sides of the equation. Now, if we Simplify that equation, we'll end up with the formula x squared plus 20x minus 50 equal to 0. Okay. Now this is a quadratic equation which is in the form of x squared plus bx plus c equal to 0. So if we compare those equations, we can find clearly a equal to 1 and b equal to 20. Actually, this is 10. So b equal to 10 here, and c equal to minus 50. Now, if you find the roots for this quadratic equation using the formula, so it will be x equal to minus b plus b squared minus 4ac divided by 2a. Okay, so we have a equal to 1, b equal to 10, and c equal to minus 50. So if we do that, the positive value of x, it will be 3.66 meter, which the correct answer is here. If you compare the answer number B, which is 3.77, which is the closest nearest value to 3.6, the value we got. Okay, so that's all. This is the solution for this problem. Okay, problem number 2 is about Kickoffs current law. So they said, what's the most nearly the current I shown in the figure? Is it minus 12 ampere or 3 ampere or 5 ampere or 15 ampere? So in order to answer this simple question, you need to define what's Kickoffs current law, which states that the summation of the current entering the node will be equal to the summation of the current leaving the node. So clearly here, if we apply Kickoffs current law, the current entering the node, we have three current, which is the current 5 ampere, the current 10 ampere, and the current I. So if we add them up, 5 ampere plus 10 ampere plus I. Now, according to Kirchhoff's current law, equal to the current leaving this node here. So the only current leaving that node is the current 3 ampere. Now, if we solve that simple equation, we can find I equal to minus 12 ampere, which is the choice number 1. The negative sign means the correct direction of the current is the opposite direction. That means current I actually is leaving that node, it's not entering the node. Here's the third problem. It's about circuit analysis. They say what's the most nearly voltage across the 5 ohm resistor in the center leg in the figure. Is it 13 volt, 16 volt, 20 volt, or 24 volt? In order to find the voltage across, or voltage drop across that center leg resistor, we need to find what's the current passing through that resistor, and then we apply Ohm's law, which is current times the voltage. We can find that voltage drop. In order to find the current, we will apply loop current method. So we will have clearly we have two loops here. So this is loop number 1, where there's the current circulating. Here is I1, and this is loop number 2, or current is circulating in this loop is I2. This is clearly the only loops we have here. So now we will write the equation for loop number 1 and the equation for loop number 2, and we solve those two equations. We can find I1 and I2, and then clearly the current passing through the center leg resistor is I1 plus I2. Then multiplied by the resistance 5 ohm, we can find the voltage drop across that resistance. So let's write the first loop equation for loop number 1. So the only voltage source we have a loop on is 10 volt, which will be equal to the total voltage drop across in that loop. So we have 10 volt equal to the first voltage drop is the across the resistance 5 ohm. So 5 ohm, and the current passing through that 5 ohm is I1 plus, and for the second resistor, which is the center leg resistance, when there is I1 and I2 passing in that resistor, so both of them are in the same direction, so we'll add them up, times 5. So this is equation number one. This is the equation number one for the loop number one. You can also write it in as 10 volt minus 5 I1 minus I1 plus I2 times 5 equal to 0, which is clearly the same equation. Now for loop number two, the only voltage source we have is 30 volt, which is equal to the summation of the voltage drops across inside that loop. So that will be 5 I2 plus I1 plus I2 times 5. So that's equation number two. Now, by solving these two equations, you can find I1, I2. So if you do that, I1 will be equal to minus 2 over 3 ampere, and I2 will be 10 over 3 ampere. So that means the voltage across the resistor in the center leg is current passing in that resistor, which is I1 plus I2 times the resistance. So that's Ohm's law, V equal to I times R. So I1, it was minus 2 over 3 plus I2 is 10 over 3 times the resistance 5 ohms. So that will be 13.3 volt. That means the answer for this problem is choice A, which is 13 volt. Here's the fourth problem, which is asking you what's the correct formula for the power factor. And in order to answer this question, you need to draw the power triangle. So if you draw the power triangle, if you have a certain load, whether inductive or capacitive, so let's say if you have inductive load, so this is P, the amount of active power absorbed by that load, and this is Q, the amount of reactive power absorbed by that load, and then summation, this is S, which is the complex power. This is volt ampere, this is in var, and this is in watt. Now this angle here, that's what they call it the power factor angle. So theta is the power factor angle. Now we all know power factor is cosine theta, or cosine the power factor angle. Now if you look to the triangle, the power factor cosine theta is B over S, which is the adjacent over the hypotenuse. So clearly that the correct formula for the power factor is P over the active power or real power divided by the complex power, which is the choice number C. Here's problem number 5. They said in the circuit shown, approximately what's capacitance is needed to achieve a power factor of 1. Now, in order to answer this question, you need to know the concept that we will have a unity power factor if the total load in the circuit is purely resistive load. In order to have a purely resistive load, so if we look here, what's the equivalent impedance in this circuit? 3 of them are connected in series, so we have R plus JXL minus JXC. Okay, so that's the total impedance because 3 of them are connected in series. Now, XL here, that's the inductive reactance for this coil, and XC here is the capacitive reactance for this capacitor. So clearly, in order to have Z, total impedance, equal to R, if JXL, this is only if XL equal to XC in magnitude. So then they will cancel each other, with the total impedance of the circuit will be pure resistance, which absorbing only active power. That means the total complex power equal to the total active power. That means the power factor, which is P over S, will be 1. That means all the active complex power absorbed in this circuit equal to is the real power. Now the problem is solved. So we need to find, okay, what's XL, which is the inductive, the magnet inductive reactance, is just omega L. Now omega is given in the circuit here, where the instantaneous value of the voltage is 100 sine 377t. That means it's in the form of 100 sine omega t. That means omega is 377, which is 2 pi times 60 hertz. So clearly that omega L will be 377 times L is 2 Henry. So that value will be 753.9 ohm. Now since XC equal to XL, so XC is 1 over omega C, so equal to 753.9. And if you substitute omega is 377, so that means C equal to 1 over 753.9 times 377. So that would be 3.5 times 10 minus 6 farad, or 3.5 microfarad, which is clearly the answer number D. This is problem number 6. It's about DC machine, and it says the DC generator turns at 2000 RPM and has an output voltage of 200 volt. The armature constant is 0.5, and the field constant of the machine is 0.02. What's the most nearly the field current produced by the generator? So in order to solve this problem, you need to understand that in DC machine, it's a rotating machine when there is a stationary part and rotational part. So there is a rotor and a stator. The rotor is the armature winding where the voltage is induced and we're getting the output power and voltage and current. And also there is a field winding where the function of the field winding is to produce the magnetic field. So because we need the magnetic field and conductors and the relative speed between them, so we can induce voltage based on Faraday's law. So that means the amount of voltage induced in the armature winding V, it proportional to the flux, magnetic flux produced in the field winding, and the speed N, which is the speed of the armature winding, and which means V equal to K phi N, where K is the proportional constant, or its constant depends on the construction of the machine. Now, since we have that, that constant is given, which is the armature constant is 0.5, and the generator is rotating at 2000 RPM, and the voltage is induced in the armature winding is 200 volt. So they need what's, we can clearly calculate the flux. So phi is V over Kn, so that will be 200 volt divided by 0.5 times 2000 RPM. So that would be 0.2 Weber. So that's the flux, magnetic flux produced in the field winding due to the field current. And clearly the flux is proportional to the field current, so that depends on the magnetizing characteristic of the material. So this is the field current, and that's as you inject more field current, you will produce more flux until the material becomes saturated. And as you produce more flux, you will induce more voltage in the armature winding. So clearly that means phi, if we put equal to KF IF. KF is a proportional constant. Here is given, they said it's 0.02. So that means if we substitute 0.2 Weber will be 0.2 times IF. So that means IF is 0.2 divided by 0.02. This is 0.02. So that will be 10 ampere. And the constant here is given in Henry because the coil inductance equal to the flux linkage divided by the current producing that flux. So L equal to the flux linkage, which is the flux divided by IF. So clearly that the flux equal to inductance, or here is 0.02 times the field current, which is we found it's 10 ampere. Here's a problem about AC induction motor. So there's a two-pole induction motor operates on a three-phase 60 Hz line-to-line supply. The motor speed is 3,420 RPM and the RMS voltage is 240 volt, was the most nearly the slip. Now, the concept of operation, if we need to discuss the concept of operation of induction motor, you need to apply input electrical power. So you apply three-phase voltage on the stator, a winding, so that will produce a rotating magnetic field in the stator winding that rotates at the synchronous speed. That synchronous speed is proportional or depends on the frequency of the applied voltage in the stator winding. So the synchronous speed N is equal to, if you need to calculate, equal to 120 times the frequency of the applied voltage divided by the number of magnetic poles. So if in this case, N is equal to 120 times the applied voltage has a 60 Hertz, so that's the frequency, divided by the number of poles is 2 poles. So that will give us 3,600 RPM. That means we produce the rotating magnetic field in the stator winding rotates at 3,600 RPM. So the magnetic field rotates at 3,600 RPM. Now, this magnetic field will interact with the rotor parts, where the rotor winding will be short-circuited, and then will be an induced voltage based on the Faraday's law, an induced current, and then induced torque. Then the rotor will start rotating. So that's induced voltage mainly depends on the Faraday's law, which is N dphi by dt. And as long as there is a relative speed between the rotating magnetic field and the rotor winding, there will be an inducing current and induced torque, and we're producing a mechanical power, so the rotor is rotating. So that is, when the machine is operating at induction motor, NR, which is the rotor speed, always less than NS, because if the rotor speed reaches the synchronous speed, there will be no relative speed between them, and then Faraday's law, because in the Faraday's law, there's no change in the flux with time, and there will be no induced voltage, no induced current in the rotor winding, and there is no torque. All right, so now if we need to define the slip refers to the difference between the rotor speed and the magnetic field synchronous speed. So S is NS minus NR over NS times 100. Okay, so we already calculate the NS, which is the synchronous speed for rotating magnetic field. So that's 3,600 minus the rotor speed is given as 3,420 divided by 3,600 times 100. So that will be 5%, which is choice A here. Please keep in mind that, again, when the induction machine operates as a motor, it always has a positive slip, which means NR less than NS all the time. Here's another problem about induction motor. You see the 4-pole induction motor operates on a 3-phase 60 Hz line-to-line supply. The RMS voltage is 240 volt. The slip is 2%. Was the most nearly the operating speed. So here they are asking what the rotor speed was, NR. Now since slip is given, and we already know that from the previous problem that NS is proportional to the frequency of the applied voltage is 120 times the frequency is 60 hertz, which is given here. The number of poles for this problem is 4 poles, so that will be 1800 RPM. This is the speed of the rotating magnetic field. Now, since S, the slip is NR, NS minus NR over NS, so that's mean NR equal to 1 minus S times NS. So already we know we have the slip that's given 2% or 0.02, and NS we calculate is 1800 RPM. So we can calculate the operating speed of the motor, which is the rotor speed, it's the mechanical speed, which will be 1 minus 0.02 times 1800. So that will be 1764 RPM, which is choice number C. And again, for induction motor, when the induction machine is operating in motoring mode, rotor speed must be always less than the synchronous speed, so that always will have a positive slip.